Thank you. Thanks, guys. Good to be back. I was here in February talking about a similar topic, I guess, but I don't think we got to the mean field game stuff. I talked to some of you in Waterloo about sort of a work that comes after this, but I realized that to present the other stuff, it really makes sense to start with this. So this is some material that'll probably be more accessible than my previous presentations. Fewer hoops to jump through to understand what I'm talking about. Anyway, happy to be here. Thanks for the invitation. So the outline of the talk, like, again, it's going to be more accessible than usual. I'll start by telling you the model I'm going to use, which obviously is going to look quite a lot like every mean field games model you've seen before, but it'll have maybe one wrinkle in it that's a little bit different. And then I'll talk about situations in which a given player's control problem reduces to an MVP, and I'll also talk about when it fails to reduce to an MVP. After that, I'll use the MVP stuff to show you that perfect equilibrium exists in a particular subset of joint policies. And then I'll try to connect it to the stuff that I talked about in Waterloo very briefly, without actually going into the details. So that's the plan. So partially observed n-player mean field games. You might think that partially observed is the key word on this slide, but it's actually the n. So the problem is going to be defined by this list of system data. I'll talk you through each of the parts, but crucially, we're going to have a finite integer n, and the players are going to be indexed by that set script n. So this is going to be the big difference, I guess, between most approaches to mean field games, where we kind of take the limit and study the limit. Instead, I'm going to stay in the finite regime the whole time, and I'm going to talk about the challenges that emerge in that situation. So X is the local state space, Y is the local observation set, and A is an action set. All these things I'm going to assume to be finite. I'll say more about the observation set in a second. That's going to be another wrinkle that might be a little bit different to stuff that we've seen before. Yeah, the next thing is that each player is going to have a function phi. So phi I is player I's observation function, and what this does is it takes an n-tuple of local states and it spits out an observation. Okay, so this is going to be deterministic rather than random, but it'll be some kind of partial measurement of the global behavior, or sorry, the global state. Talk about that more in a second. This part's normal. The cost function is going to depend on the local state, some empirical term, and an action. There's going to be this thing that I call ploc, and this notation here means a transition kernel on X given the rest of this stuff. So action, state, mean field, and action. So that part, I guess, also pretty conventional. I'm going to use gamma to denote my discount factor, and nu 0 is just going to be some initial distribution on the global state. So I'll talk about the global state in a second, but just a point in that Cartesian product indexed by the players. Okay, so this is the list of things defining a partially observed n-player mean field game. I should also tell you what play looks like. So ignore the bottom half of the screen for a moment. At time t, a given player will have local state xit. And then the thing I've been calling a global state, this is just a collection of all individuals' local states, okay, the tuple. The mean field state at time t is going to be denoted mu sub t. It's going to be the empirical distribution associated with the global state. Okay, I'm going to come up with a slightly different notation to make this explicit, but mu t depends on xt. Okay, this thing is a random variable, and it's defined using this one. Okay, it's just what you expect it to be, of the proportion of players in the set B. Is that okay? Nothing unusual so far, right? Any questions? Definitely feel free to interrupt. So with those state things defined, the player is going to make some observation on the global state. I'm going to denote that observation yit for player I, and it's going to be, again, viewed through this observation function of phi. Player I is going to pick an action. Player I is going to incur a cost that depends on its local state, the mean field, and its action. And then it's going to undergo a state transition. I haven't written this here, but once states and actions have been picked, each player's local state transition is going to be conditionally independent of everybody else's. Okay.
Could you make that precise, perhaps on the board?
Sure.
I brought some pens.
Yes, thank you.
A very quick question.
So
Can I ask a quick question?
you tell me if it's big enough.
Yeah.
So this is.
I think there's the speaker on their side is muted.
Exactly
So
right.
let me give
One.
them a call.
One, N C plus one is equal to S N given X D AT. So these are meant to be bold. This is like a global state. This is like a joint action. Oh, did we cut out? We lose somebody?
Hi, Rob. Yeah, hi. Oh, Mindy
Yeah,
has a question.
Peter, can you
Oh,
hear me?
I can hear you. I can hear you now. If you want to try. Again.
Okay, good. So for your observation, you have y equal to the function phi super I.
Mm-hmm.
So it's just like a deterministic rule, or actually some kind of transition. Because normally, when we talk about the partial observation, you have a transition relation. Given xt, you have you can observe which output with what probability. So can
Yeah,
you?
no, this is deterministic.
Okay.
And I'll say more about it in 1 second. Here, I'll jump ahead. I'll talk you through a few different options of phi I.
We have one solution. You mute your microphone and Borna angles his sits up front, so your volume comes through his microphone.
Sure. Yeah, I don't understand what's going on this computer. Anyway, my apologies for the technical issues. Maybe I'll take that question again. Also, it's giving me an error when it says
Okay.
I generally use like.
So unlike your partial observation modeling, here you just have a deterministic mapping. Okay.
That's correct.
Oh, okay. Okay, go ahead. Yeah.
So I'll try to clarify this point in a minute and actually give some specific deterministic observation channels. Like they're degenerate transition kernels is what you're asking, right?
Yeah. Okay. Good.
Maybe 4 slides. I'll try to revisit that question.
Here's a point.
I feel like if I plug one more thing in my computer, the whole thing might blow up.
Oh, that's just a pointer to the screen.
It's just a laser pointer.
Oh, I thought you meant to plug into this. Change the slides. That's great. Okay, perfect. Thank you. So the question a minute ago, Peter, was, can you formalize that thing that I said that's not written at the bottom?
Yeah.
At the bottom here, I've written that each player is going to undergo a state transition, and that's going to depend on this transition kernel PLOC, with xi, mut t, and ai being the things that determine the transition probability.
Right.
Well, I was trying to say that that's fine for one player, but you ask how does the collection of players evolve, and I was just saying that should have a product structure. That should be conditionally. So given this thing, it should be product over each of the players as PLOC business. XJT, mut t, AJT. This is so quick remark on notation. What symbols do I use? Player indices are going to go in the superscript. Time indices go in the subscript. Usually, if there is a subscript time index, I'm talking about a random variable. Not always. But if there is not a time index in the subscript, then you can pretty much bet that this is not a random variable. Okay. So these are just generic points in the set. And another thing I should say, bold symbols are always meant to be tuples with, entries for each of the players. So that's what this last point says. So if you see an unbold symbol with a player superscript, that thing is going to be player i's component of the corresponding bold symbol. So I said I was going to define a function. This thing, the upright version of mu, this is going to map global states to empirical distributions, defined the same way as before, but now the dependence on the state is explicit. Okay. So I guess I can use this laser pointer. This thing is a function. You feed it a global state. That global state sums over all the players and tells me what proportion of players divided by n are in state B. It's set B, where B is some subset of the global states. Okay, so that's what this function is. And then this thing, empirical n, is meant to be the set of all probability distributions that can be obtained from n point masses. Is there any questions about this? This is going to show up in a slide about observation channels in a second. So if you do have a question, come back. So Minyi's question a minute ago was, can you tell me about this observation function? And I was telling you observation functions are going to be mappings from global states to this observation set, but I haven't yet told you what the observation set is. Okay. And throughout this talk and my works, I'm going to refer to the pair of y and the functions phi I as the observation channel for the game. So here are 4 alternative observation assumptions that you can impose that I've seen showing up in the literature, except for the third one. The third one, I think, might be a natural generalization that might not have been talked about before. So the first one is the obvious and least decentralized of them all. In this one, your observation set y is going to be equal to the set of global states. Your observation function is just the identity. It tells you what everybody's local state is. And you get to see the full global state information. So I'm going to call that global observability. It is what you think it is. This one might be the most common. And if it's not the most common, then local will be. But in this one, the observation set y is going to be the local state space cross the set of empirical measures made with n players. Okay? And then the third bullet is really the thing that you should read. A given player I will see its own part of the global state, so it'll see its local state, as well as the empirical distribution associated with the global state. So if you prefer symbols, give me a global state, well, I'll see SI, and I'll see the empirical distribution, but I won't see any other individual's local state. So I'm going to call this setting mean field observability, and we're going to spend most of our time here. So is this okay? This should look familiar. The next one's going to look a little less familiar, but if any of you have seen this before, please tell me. I'd love to attribute this to somebody. This I'm going to call compressed observability. And the idea here is I'm going to get to see my own local state as before, but instead of seeing the entire empirical distribution, I'm just going to see some compressed version of it. So imagine you've got something like Google Maps on your phone, and you're planning your route, and it shows you there's red on this road and blue on this road and yellow on this other. It's not telling you what proportion of drivers are on a given road length. It's telling you whether it's high, low, or medium. Okay, so it's like a compressed version. Okay? So in this case, the observation set is my local state space cross some set of symbols, which I'm just going to use integers for symbols. And I'm going to see my local state, and then I'm going to see the mean field pumped through this compression function f. So of course, if k is the size of the empirical distribution set, 2 can be written as a special case of 3, where you have no compression. Like if f was the identity. So has anybody seen this before, number 3? Or is this my doing? I think you can kind of imagine that this seems like an appropriate thing for some applications. And the final one, again, this is might be the most common as well. I just see my own local state. I don't see anything else. So there's a Minyi. I hope that clarifies a little bit what kind of observation channels we're going to be considering. There's no noise in my reading of the global state. It's just loss. Like I might lose some stuff, but there won't be any noise other than that. Okay, so that's not all the information that a given player has available to it. That's just the information about the state. I can also talk about what the player can access when it chooses to make a decision. And to do that, I'm going to distinguish between system histories in bold and observable histories, unbold. So a system history tells you the entire past of global states and actions for each of the players, these bold A's. Meanwhile, player I is just going to see its own observation, its own action, and what cost it incurred, all the way up to the present time. So this distinction is just about what's really happened, bold, versus what player I has seen. Critically, player I doesn't see what actions the others have taken, and it doesn't see what costs the others have incurred. And whatever it can see about the global state is already encoded in its Y variable. Does That's the observable histories. And then the policies are what you expect them to be: time varying, history dependent policies. Sequence of transition kernels on actions given histories, where you pick your action according to the history that you've seen. All good? I use pi I with no subscript. This means admissible policies for player I. I'm going to talk more about what policies I'm going to focus on in 2 or 3 slides, but this is the set of all, if you write a learning algorithm, it has to belong to this set. So again, just to emphasize, actions and costs, these are not global information, these are private to the players. So give me a policy for each of the players, and this is the cost criteria I'm going to deal with. Infinite horizon expected discounted by gamma. So bold pi is the joint policy, initial global state is distributed according to whatever the third argument is here, and actions are chosen according to the policies. This should be pretty standard, I hope. Any questions, we can come back. With this definition of the objective function, I'm going to define 2 notions of best responding, and I really think you need 2 here to deal with the issue of partial observability. Okay, you can best respond to the policies of the other players with respect to an initial distribution, or you can best respond with respect to every distribution. Okay, so in the first case, I'll say your epsilon best responding with respect to initial distribution, maybe with respect to new. In the second case, I'll say you're uniformly epsilon best responding. This distinction is really important, so if we need to double click on this, please interrupt. What's the analogy to think about? Consider a partially observed Markov decision problem. If you have a policy that does well for one initial distribution for the hidden global for the hidden state, it might not be very good for another initial distribution. So that thing would be, epsilon optimal with respect to something, but not something else. On the other hand, you might be good for any initial distribution, in which case you'd be uniformly epsilon optimal.
Your information set is still the same, right?
Yeah, these are just definitions rather than But yes, your information set in both of these, you're infamizing over the same set of policies, and the set of policies was defined using those history things that I presented a moment ago. Where was it? These things. So that is set up to this point. So for each of these notions of best responding, I can come up with a corresponding equilibrium. The first one is going to be equilibrium with respect to an initial distribution, in which case everybody is happy provided the initial global state has distribution new. The next one I'm going to call perfect epsilon equilibrium, and this is for any initial distribution. So there's a little bit of a mixing of language here, but this is I guess, inspired by subgame perfection or something like that. Or if you're more interested in Markov games, something like Markov perfect equilibrium, where it really should be optimal for any initial state, right? And I'm doing that by conditioning on the initial distribution. I'm going to pause in case there's a question.
In the MFP setup, we have a Nash equilibrium, which is called strong Nash equilibrium, where even if you're given all information, you're still doing as well as you possibly can.
Like if you have a different policy set that's more informative, you mean?
That even if you were told everything. So
so you replace pi I by something that contains pi I.
Yeah, all of the pi sets, right? So, and I've provoked audiences by saying, does anybody seen you sort of refer to anything with this form of strong Nash equilibrium? And I never get a response.
So I guess today, the result, this definition might not cover this, like what you're saying might be stronger than this, but the result will ultimately be effectively that. So
good.
So there's a bit of subtlety, like I'm not saying this definition is equivalent to strong Nash. No. But the MDP stuff.
I haven't even ever heard that term you just accepted.
Oh, really? It's good. Thanks for bringing it to my attention. I'll take a look and I'll see how they compare. Okay. So I've stopped for questions because now we're kind of moving into the second part of the talk. So far, each person is facing some stochastic control problem. Okay, but we don't know what it is yet. It's partially observed, and it depends on the policies of the counter players. Excuse me. Questions like, how does it depend on the observation channel? How does it depend on policies of players? Do equilibrium exist? Where? How do I find them? How do I characterize them? That kind of thing. And I can ask kind of similar questions like, do best responses exist in particular subsets of my policies? How do I find them? How do I characterize them? If you ask me, these are like the natural things to begin with when studying a slightly different model of a game. So the policy subset that I want to give attention to is this thing that I'm going to call memoryless stationary policies. If you've seen Markov policies in an MDP, this is like a Markov policy, except for now, not necessarily facing a state variable, so I'm not going to call it a Markov thing. Basically, as long as you condition only on your most recent observation, and you do it in a time invariant way, such a policy is going to be called memoryless and stationary. Intuition is clear. In symbols, that means there exists some transition kernel on actions given observations, such that condition on the whole history pump through your policy, that's going to be the same as condition only on the most recent symbol and pump it through this transition kernel. Okay, so I'm going to actually identify my set of stationary memoryless policies with these transition kernels directly. I'm not going to refer to the entire history anymore, as long as I'm talking about a memoryless stationary policy. And then if I put a subscript on the policy set, that means I'm talking about stationary policies. And I'm not even going to say memoryless anymore.
But it will be memory.
That's the, yeah, implicitly.
Sorry, what is this?
Script P, set 1, set 2. This means transition kernels on A given Y. So an element of P on A given Y is a collection of probability distributions that depend on Y. So for each Y, I get a probability distribution over A. Yeah, so that's what this notation is. My pleasure. And then I guess this should sort of suggest the same thing. Like give me YIT, that's probability distribution over my actions. So I'm facing a stochastic control problem, but why should this thing be a controlled Markov process? A priori, why? There's no reason to believe it should be. This shouldn't be a real state variable in the sense of sufficient statistic for decision making, controlled Markov process, that sort of thing. So why in the world should my best responses to something be memoryless and stationary, or just memoryless? You know, it might even be time. There's no good reason to believe this either. Okay, so I want to emphasize that this problem might seem more obvious than it is, but like you should juggle these questions before thinking everything's too easy. Now, if we have global observability, things do get a lot simpler, right? In that case, the game that I was describing earlier is a stochastic game with full state observability. If the other players use stationary policies, then player I faces an MDP. That's huge. And the existence of perfect equilibrium instead of stationary joint policies, that's well known, the 60-year-old result. Okay, so that's with global observability. If you don't have global observability and instead you've got, you know, mean field observability or compressed or local observability, and the number of players is finite, the mean field term will evolve randomly, right? This is no longer the infinite regime thing where it's a deterministic flow. It's going to be a random evolution. What does that mean for player I? Well, its costs, its transitions, depend on some potentially non-Markovian thing that's random. So you can't just use standard MDP results to analyze player I's control problem necessarily. You're going to have to prove it, and then that's going to have to rely on some conditions, which I'll describe in a second. So the existence of equilibrium in a given subset, especially memoryless stationary equilibrium, not for free. Here's a nice little quote from a paper from 5 years ago, talking about with partial observability, you bump into these problems. Okay, I'm sure in the last 5 years, some things have changed. So this is part of the reason why I wanted to come and give this talk. You can tell me what you've seen in case I'm glossing over something that came out. How am I doing for time, by the way? I shouldn't labor them too much. We got probably half an hour. So if we do go to the limit, n is equal to infinity, this is kind of like the conventional model. This thing has a deterministic evolution. Now we're just in the classic MFG setting. Players will face a possibly time-varying MDP, but an MDP nevertheless. Suddenly, the mu t sequence, you can just subsume that into the decision problem. The local state information is all you need, with the caveat that it's time-varying. So this is really different than finite n. That's why I said at the beginning that the important thing was that n is finite. Okay. All right, now time for the rest of the talk in half an hour. So I want to leverage what I know about MDPs and POMDPs to talk about the mean field game. So I want to understand if and when a given player faces a POMDP, and if not, when we can guarantee that it faces an MDP with additional assumptions. To do that, I should study how these things all evolve. You know, conditional evolutions and terrain variables. Okay. So what does it mean to face an MDP, or excuse me, a POMDP in this setting? Well, if the other players are following some policy pi minus I, then I might face a POMDP with hidden state process bold xt controlled by my action set only. Sorry, my actions only. If the Markov condition holds, in which case this thing's hidden state process would be the global states, and then my measurement sequence would be my local observations. Okay, so I'm trying not to go into too much formality in this, but as long as I can get sort of this conditional probability where there's an h here and replace it by this conditional probability where there's an x here, and as long as this thing is time homogeneous, then I'll be facing a POMDP. Any objections? And the reason, I guess, for this is that this thing is cost relevant. I don't need more information than this to predict my cost. So it really depends on how the policies influence the evolution of that local state. And again, I'm saying hidden state. This isn't meant to be observed at this point. Okay. Unsurprisingly, if the other players use stationary memoryless policies, then player I is going to face a POMDP, where the hidden state is given by the global state and the observation sequence is going to be given by the observations that the player receives. So I can describe how you show that. Let's study the conditional evolution of the next global state. Now note, this isn't the actions of all the players. This is just the action of player I. Okay, so how do I analyze that? I'll use iterated expectations. I'll condition on the actions of the other players. Well, condition on the actions of the other players. So we get a blue term and an orange term. Nothing interesting has happened yet. So Peter asked earlier, what did you mean when you said that conditionally their local states will evolve independently? It means that it takes on this product structure. This is what I have written on the board here. I'm not sure if this is still good. What's the probability of a joint action being selected given a particular shared history and an action for player I? Well, I don't get to see what action player I took, so player J will just condition on its local history. But because player J is using a stationary policy, you can drop this time index off its policy, and you can replace the entire history by its most recent observation. What is player J's most recent observation? It is, I think this should be, sorry, in there is the wrong symbol, but it views the global state through its observation channel. Okay. Finally, once we've made these changes, I can go backward and say, well, this doesn't depend on the whole history anymore. This just depends on xt. This only depended on most recent state, so I can replace that there. But of course, we can recognize this is simply this final term, which is the thing I was trying to show. So a lot of symbols, don't get lost in it. This should not be a surprising lemma. If you have any questions, please do raise your hand. So if everybody else uses stationary policy, then I face a POMDP, hidden states global, observation process, observation process. Now, of course, using that same line of deduction, if the other players are using policies that are not stationary, in the sense that they depend on the whole history, I can't actually do this step. Here we had the player J picked its action by conditioning on its history, but I can't drop the time index if that thing is non-stationary. And if that thing is history dependent, I can't replace the whole history by the most recent observation. So this step doesn't hold anymore. And so the controlled Markov property ceases to hold. Okay. So it was crucial here that the counter players used a stationary policy. Does that make sense? So that was about POMDPs. I'm going to start talking about MDPs in a second. But this is really the start. What would it mean to face a fully observed Markov decision problem in this partially observed setup? Well, it would have to be that your observation sequence tells you everything that you need to know to make optimal decisions. It would have to be a controlled Markov process controlled by your action set. And it would have to satisfy some time homogeneity condition, because I want the MDP to be. So the first question is my observation variable YIT a good summary statistic, or excuse me, sufficient statistic of the entire history of the system? Does this conditional expectation hold? Okay. That's the first thing about cost relevant histories. The second, does it satisfy this evolution rule? Okay, now I'll point out that the right-hand side here depends on t. So the final thing would just be to ask, does it actually not vary with t? So if all three of these things hold, I'm not going to formalize this more than this, but then I can show that player I actually faces an MDP, a time homogeneous MDP.
So the counterintuitive part, or the key aspect, is that bold-faced H sub P is a huge history.
Yeah.
And that's the work.
It's everybody's state history, everybody's action history.
And then conditioning, and so that's huge, it's very strict.
Yeah, this is, I mean, the question mark is to say, why should this hold? Why would YI tell me everything I need to know about the history of the system? Yeah, this will not hold for plenty of, policies, observation channels, and so forth. Like, if all of this holds, then I can throw out the history and I can make my decisions using YIT alone. That's where the MDP comes. So yeah, thank you. All right. So the first one, again, it's not obvious at all, but it's going to be easier to talk about, right? Because I can just look at my cost function and see how that depends on the global history, right? So this one will be easy to talk about, even though it's not necessarily always going to hold. The final one about time homogeneity, well, this only comes after I show that the controlled Markov property holds. So I'm going to skip this for the time. I'm going to skip this for the time because it'll fall out of this analysis. So is YIT going to be a controlled Markov process? So this is a theorem, small theorem. It's not going to be groundbreaking, but I think it's very interesting. Give me a partially observed n-player game with mean field observability. So I get to see my local state and I get to see the mean field at the time. Suppose that the other players use a symmetric and stationary policy. What does symmetric mean? It means that basically I'm using the same policy as the others. What does stationary mean? Everybody's individual policy station. Then player I is going to face a controlled Markov process. Sorry, an MDP, and the controlled state process for this MDP is YIT. Okay. So I'll show you the argument, the line of argument. We might have to skip a few just in the interest of time, but we're going to see that all three of these are strictly necessary. If you relax any of them, I can give you an example where it stops being an MDP. So how might we approach proving this? Well, really what I want to do is the third thing. I want to show that conditioning on YIT's value and AIT's value, I have just as good a prediction as if I conditioned on the whole global state. Right? So if I can do that, then we're done. But how am I going to do that? Well, I guess I should talk about the conditional evolution of my observation symbols based on the underlying global state. Okay. So conditioning on YIT is conditioning on, I know something about the global state, but I don't know very much. So what would I know if two global states gave rise to the same observation? I'm going to actually argue that it gives me the same probability distribution for the next observation. And then to do that, I'm going to argue something about when two global states give the same observation. So I presented that backward, but this is the line of approach. So here's a question for you. If I tell you that we have mean field observability, which means that player I gets to see its state and it gets to see the mean field, when will two global states, S and bar S, when will these two things give rise to the same observation? This isn't a trick question. The answer will be obvious after we say it, but I'm curious if anybody sees it right away. Obvious.
They give rise to the same actions by all the other players.
So this is just the global state. The action part is that doesn't actually play in, because this is just a reading I get. So I'll answer it for you, but confirm my answer if you can in your head. These two things will give rise to the same observation symbol at player I if the second one can be obtained from the first by permuting the local states of all the other players. All right, so
So that doesn't mean they carry out the same control action.
the control actions, no. This is just about states.
So their responses though.
So I tell you what state that you're in, and I tell you how many people are in each of the other global states. You know, a third of the people are in that state, half the people are in this state, 1/1000th of the people are in this state over here. Now, I tell you the global state changed, but the distribution of everybody has remained the same. What do I know about both those things? Well, there's still 1/1000th of the people over there. I don't know the identities of these people, but I know 1/1000th are in the third state. I know half are in that first state, so forth. So in order to do that, I have to move people around. I have to shuffle them. But the number of people in each local state has to remain the same, which is where this permutation idea comes in. Okay. So in symbols, give me a sigma, which is going to be a permutation on these players, such that it leaves player I's part fixed, right? Like I know that I'm in state SI in both these two, so this permutation really can't change where I am, but it can change where all the other players are. And for a given player J, its local state in bar S is going to be given by player sigma J's local state in the other state. So a little bit of notation. I'm going to actually make it worse and say sigma acting on a global state is when you shuffle those players around according to sigma. Okay. So this is super important. Like I really want to underline how important this is. It lets us do something that's going to be kind of dense, but what is this set? This set is the set of all global states that give rise to the same observation at player I as the global state, old S. Okay? It gives me a way of writing this set that's a little bit more useful for analyzing conditional probabilities. It says that the set of all global states that give rise to the same observation can be obtained by just permuting S. Okay? Now I'm going to use the symmetry of the other player's behavior to analyze the conditional probability equations. Any questions? Super dense, apologies. Lots of notation. We can't help it. Okay, so now the next thing I'm going to argue is that if two global states do give rise to the same observation, then it should be that the conditional probability for the next observation, well, those two measures should be the same. Okay. An adversarial audience member would say, what? That makes no sense. Why should that be the case? And to show that, I'll actually show something kind of incomplete, but this is the thing that you use to prove this top line. You say that what's the probability of the next global state being X given the current global state is S? Well, whatever that probability is, if I permute the first global state and make it sigma S, then look at this here. Permute the terms in this product, that's the same probability as going from sigma S to sigma X. It has to be. That's because we have a finite product and finite products are invariant under permutation of the terms. Okay. Another dense equation, but what this is saying is that give me some information about the next global state, I can infer something about the next observation of player I. And excuse me, from that stuff I was just talking about, the global state being a permutation of the other will give rise to the same observation. So this is really dense. I should probably skip through it and not wear us down anymore. But if you've shown all that stuff, it actually comes through quite quickly. So I'll ask if you're interested in this. We have a paper where we read it, the proof in full. It might be a little bit easier to follow if you have 2 pages of attention rather than 3 slides. Okay, so I just showed you that. I'll show you the theorem one more time. If the rest of the players follow a symmetric, stationary policy, and if you get to see the mean field, then you face an MDP. This thing is actually going to be all that you need to make your decisions. The YIT sequence is sufficient for decision. It is going to be natural to ask when we can relax any of those conditions. Okay, can I get rid of symmetry? Instead of mean field observability, can I get away with less? Can I throw out the mean field term? Remember, as you go from to n is equal to infinity, this whole stationary mean field equilibrium solution concept says, fix mu star, all I need is my local state. Like I can make optimal decisions using that. So does that hold when n is finite? How about some examples? So what's this diagram trying to tell you? Here we've got 3 states, 0, 1, and 2. When you're in state 0, you will randomly either go to state 1 or state 2 with probability almost a half. And then with some small probability, you'll just return to state 0. Your action doesn't matter for your transitions out of state 0. When you're in state 1, you get to pick whether you go to state 1 or 2, or 0, I suppose, if you felt like it. And if you're in state 2, you again get to dictate what state you go to. You can either play action A is equal to 1 and go to state 1, or you play action A is 2 and go to state 2. So this is meant to be like a transition probability diagram. Is this okay? You understand how the transitions work? I haven't included transitions back to state 0 because they don't matter. So say we've got 3 players. They're going to play a mean field game on this. The cost function doesn't matter, but the local state space and the local action space are what I just showed you on the previous slide, 0, 1, 2. We have mean field observability, and I'm going to look at the problem from player 1's perspective. And I'm going to assign a policy to player 2 and player 3. So player 2 is always going to play the action corresponding to the state that is present in. Okay, so if he's in state 1, he plays action 1 to remain in state 1. If player 2 is in state 2, it plays action 2 and it remains in state 2. So player J is the state type. Understood? Meanwhile, player 3, which I'll label K, it's always going to play action 2. It's always going to want to go to state 2. It doesn't matter where it is. So if it's in state 1, it chooses to go to state 2. If it's in state 2, it chooses to stay. Okay, and then initially everybody starts in state 0, right? From which they can return randomly, or they might get thrown to one of the other states. So an observation for this problem is going to be what state am I in, and then what proportion of people are in the other states. Okay. So suppose at a given time, I'm player 1, and I can see that, well, I'm in state 0, and there is 1 person in each state. That's what this probability vector is telling us. Well, what's the probability that all of us end up in state 2 tomorrow? Given that I'm in state 0 and there's 1 person in each state, what's the probability that all of us end up in state 2 tomorrow? Well, I told you that there is a player of the type that always chooses action 2. So he'll try to drive to state 2. And there's a player that always chooses to stay. Of course, there's a probability that I get thrown to state 2 because if I'm in state 0, I don't have any influence on my behavior. So what's the probability that we all end up in state 2? Well, it's the same as the probability that the player who chooses to go to state 2 is not yet in state 2. Well, it might not be the same. That plus the probability that I transition to state 2. But if you believe me, I swear it's true. That probability is positive. Okay, and the way to see that it's positive is you just ask, what's the probability the guy that likes to be in state 2 is not in state 2 yet? So that's positive. However, if I see that in the last period, everybody stayed where they were, well, then I know that that guy's already in state 2, and I know that the state type player is the one that's actually in state 1. Okay, so I'm conditioning on today's observation and yesterday's observation. I can see that nobody moved. I didn't have a say in where I went, but the other two guys did. And they chose to stay, which means everybody's happy where they are. So the person that's in state 1 is never going to choose to move by the definition of this policy. So in fact, if I can see that nobody moved yesterday, this probability that tomorrow everybody's in state 2, that'll be 0. Okay. What that means is that we get different conditional probabilities when I take history into account. The Markov property fails. So in fact, by relaxing symmetry of the joint policy, I've lost the controlled Markov property. I don't face an MDP anymore. This is just putting that to a slide. Even with mean field observability, even with stationary policies for all players, it's no longer an MDP. Okay. What about if I keep symmetry, but I throw away the mean field observability part? Just make sure I'm doing okay on time. Oh boy. All right. I'll motor through the next part of this. In this example, we've got 10 states. You can imagine them on the line.
Good.
Goodness. Said I was going to motor. Started going much slower. So at a given time, say you're here, you've got some probability distribution. That's got a mean, and I'm in this state. Okay. With some probability, I will go back to the next integer that is round up above the mean, or I'll go all the way to the right extreme. Okay. This is my actions have no influence. This is just an exogenous process driving each player's local state. I only have local observability. My goal is going to be to estimate the mean field. Right? The better I estimate it, so my action set is just guesses about what I think the mean field is, the better I perform. So I really do want to track the mean field. And I'm wondering, is it enough to just use my local state to make decisions? And the answer is, of course, going to be no. If I'm trying to track the mean field, but I don't get to see it, then I should remember what's happened to me in the past. Okay, because my evolution depends on the mean field. So a second slide just to summarize this. My local state either goes to the right endpoint or it goes to the mean of the last mean field. What this means is that the mean field sequence is increasing, it never goes down, and decreases in my local state only happen when they tell me something about what the mean is. So if my local state goes from here down, then I automatically know, oh, the mean is not way back here. It's whatever I just transitioned to. So is it a controlled Markov process? From what I just said, no. Because suppose for some omega between the endpoints, I want to know what the probability of me going below omega is. So I don't know, make omega 2 here. What's the probability that at the next time period I go to state 1? Or make omega 3 or something. Basically, initially, if everybody's uniformly distributed and I'm way over here, it might just be that I ended up on the wrong side of the mean, and I might get pulled back to the mean. The mean might be over here somewhere. I don't know that it's not. This has positive probability. But if I condition on the past, and I see that recently I went from M to something back to M, automatically I know that the mean is not left of the thing that I just transitioned to. So here I've chosen omega plus 1. But I went from M at time t minus 2 to omega plus 1 back to M. That means at time t minus 2, the mean was at least omega, or even bigger than omega. And this thing is non-decreasing. So I can never go below omega. So this probability becomes 0. Okay, so you could not relax symmetry even with mean field observability. And if you didn't have mean field observability, even symmetry is not enough. Okay, so I think this is a pretty comprehensive description of when you face an MDP in this model. Okay, in general, you have to have mean field observability and symmetry of your counter players' policies. If you make additional assumptions on the game, maybe not, maybe you can get away with less. But if you want to stay as general as I've tried to stay, then you need all these things. Okay, so this is the part that I'm going to motor, and this is the part that I was actually going to ask Peter, in case you've seen a theorem like this before, you guys too. Give me a partially observed mean field game with mean field observability. For any positive epsilon, or including 0, there exists a stationary perfect equilibrium. What does that mean? Everybody's using stationary policies, and it's a uniform best response to my counterparts. That optimality is not just over my stationary policies or my Markov policies or whatever. In fact, it's optimal over my whole set of history-dependent time-varying policies, and for any initial distribution. So this is like kind of an interesting result, right? Like it's quite a lot of optimality simultaneously being guaranteed, and it's also true for epsilon equals 0. So there's no approximation. So it's kind of an interesting result, but the actual proof sketch is like 60 years old. I didn't do anything groundbreaking. Don't tell the referees that, but so to do this, you're just going to define a map that maps my set of stationary policies onto the stationary policies for the remaining players. Okay, so pi I is going to map to a policy where everybody follows pi I. Okay, when I'm playing against this thing, I'm facing an MDP, which means I have, stationary best responses. So then I can define a set valued function that takes a policy of mine and sends me to my stationary best responses. Okay, so now we're digesting a lot of stuff into one bullet, but this set's going to be non-empty, compact, convex. I think this should be upper hemi-continuity. But then you can apply Kakutani's fixed point theorem, which means there is some function, some policy that is in its own best response set. That's going to be an equilibrium. Cool. So the challenge was partial observability. This holds for any number of players in any epsilon positive. Like I didn't have to say make epsilon positive and take n big enough, then you get, epsilon equilibrium. No, this holds for every epsilon. I'm not, like I said, this isn't like earth-shattering stuff. I just thought it was interesting because of the partial observability. And the fact that I was just showing that this MDP thing fails when you relax these other conditions. Okay, the conclusions I'm going to skip because people might have to run. But I want to make a comment. The only other person that I've seen give results similar to this, there's a 8-year-old paper by Anoop Biswas, and in that paper he considers not discounted cost but average cost. And sort of one discrepancy I noticed was that I'm talking about optimality over all history-dependent policies, whereas the equilibrium that Anoop proves is over Markov policies only. So time-varying policies that depend only on your local state, in his case. But from that discussion I showed on the earlier slides, you can't really throw that stuff out. You actually do need to use as much information as you can get. Okay, so if you do have to leave, I'll let you run. There are a few more slides.
People will run if they have to, so feel free to.
If anybody in the room has to. Okay, so in summary, things do really change when you have a finite number. And this partial observability thing turns out to be kind of interesting in a meaningful way. It depends on the channel that you have, depends on the policies of your counterparts. That determines what kind of stochastic control problem you have. Okay. Now, why did I bring this up? Right? There's plenty of models already. Why recast something? And the answer is that I wanted to talk about problems where you're doing learning, where your policy is something that reflects an iterative learning process. Okay. I wanted to study a system where you've got a large number but a finite number of agents, each of them learning using local information. The finiteness is important, right? There's lots of papers on learning in mean field games where you pass to the limit, but I wanted the finite thing because I want strategic interaction to be, non-trivial. Like I want it to sort of be a meaningful coupling, not just a weak coupling. So in such a setting, we've got very little information about the system a priori. Okay. Now, in a world where I have to figure out how to drive to work, I might have different beliefs than somebody that lives in my neighborhood. So the roads that I pick might be different. So the policies that we use really, I don't know. I don't think that they should all be the same in a learning setting, that is. In a decentralized learning setting where we learn using our own information, I don't want to take this approach where we impose that each of these people uses the same policy. So this is a little bit different than other papers on learning in mean field games. The next thing is that even if we did use the same policies in the sense of time varying, history dependent policies, well, the histories that we see are going to be different, right? So the distribution on my action is going to be different if I'm using a learning algorithm. It's a time varying policy. So really, I expect to see heterogeneous behavior. So this was what I was presenting in water, was something that was trying to approach this problem. And to approach this problem, I actually had to pass through the symmetric stuff that I talked about before. This was not meant to be a learning talk. So that inspiration really should just serve as inspiration. But understanding what happens in these three decentralized settings really can help us make sense of decentralized learning. And I guess one of the takeaways I want to give is that things really do break down with finitely many players. What did we do? We studied this POMDP connection the best we could, and we studied what would happen if players, did naive Q learning, where they treated YIT as if it were a sufficient statistic, a controlled Markov process. This is not fair. We just talked about this. This is like not a reasonable thing to do. At least it's not a justifiable thing to do. But it turns out there's a bunch of applied work where people look at a POMDP and then they treat their most recent observation as if it was a state variable. And sometimes it works really well, but why does it work well? I haven't really found very many explanations that try to put this on a theoretical framework. And that was kind of what this other work that we did was. We study the limits of these learning. We can characterize it now. And then we can define subjective equilibrium and things of that nature. That's what these works were. If you remember my talk in Waterloo, it was a very dense talk because I tried to introduce probably 3 or 4 different ideas simultaneously. I thought maybe it would be good to come back and clean up the mess that I made back then. So yeah, that's the extent of it.
You're always welcome to come back.
Yeah. All right, that's all. If there's any questions, thanks for listening.